Okay, we are recording. And what I'd like to do, we talked last time about section 13.3 in our last class. We talked about the fundamental theorem for line integrals. And we learned that if we have a conservative force field or conservative vector field, then finding the work that that force field does in moving a particle along a path in the vector field is very easy to compute using the fundamental theorem of line integrals. So we looked at a problem where we had a force field or a vector field in two-dimensional space, and we found the potential function. Now, what is the potential function? Well, the potential function f is the function f such that the gradient of the function is equal to the vector field, right? And so that function f is called your potential function. Okay, and some vector fields are conservative and have a potential function. Other vector fields are not conservative and do not have a potential function. And if the vector field does not have a potential, if it's not a conservative vector field, then you have to compute, you have to compute this integral here, which is the work integral that the vector field does in moving the particle along a path C in the field. That work, you would have to use section 13.2 concepts. You'd have to work, you'd have to work it out using section 13.2. But it's always nice if we do have a conservative vector field, because then we can use the fundamental theorem of line integrals. So let me give you a moment to copy this example down, and then we'll go over it. This is now one where we have a three-dimensional conservative vector field. Okay, so now you'll notice that in this problem, they tell you that this vector field is a conservative vector field. They're not saying, hey, is this vector field conservative or not? And the reason is you do not currently have criteria to determine if a three-dimensional vector field is conservative or not. You do have criteria which can determine if a two-dimensional vector field is conservative or not conservative, but you don't have one yet for the three-dimensional vector field. But we will learn in section 13.5, we will establish criteria to determine when a three-dimensional vector field is conservative or not. So we want to find the work done by this conservative force field in moving the particle along the curve C. And the curve C is actually a line segment from 0 to -1 to 5, -1, 1. And normally to find the work, we would need to find the parameterization for that line segment. But because we have a conservative vector field, we can utilize the fundamental theorem of line integrals, the f that's the abbreviation. Hold on, let me just, one moment. Yeah, the FTLI, fundamental theorem of line integrals, says that the integral, the line integral, where the vector field is the gradient of some function, that line integral can be found by computing the function evaluated at the endpoint R of B minus the function evaluated at the initial point R of A. A and B obviously are time values. Okay, so that's, well, essentially it means find the potential function f and substitute in 5, -1, 1 for this R of B, and and then substitute in 0, 2, -1 for R of A, and that is what R of A would be. It would be that coordinate, and then take the difference of the function values. So, okay, let's find the potential function. So since the function itself is conservative, we can find a potential function. And again, what is a potential function? It's a function such that the gradient of that function is equal to the vector field. Okay. So let me just go back for one moment. Let me go back for one moment. If the gradient of the function equals the vector field, okay, then this gradient of the potential function is equal to the vector field. Then this work value from that line integral can be found using the fundamental theorem of line integrals. Okay, so, okay, here we go. So, okay, so we have to make use of this equation. The gradient of our potential function equals the vector field. Well, the gradient, you know, how's the gradient defined of a function? It's the vector of partial derivatives of f with respect to x, y, and z. It's the with those components. Okay, so let me see here. I have to do a little erasing. Okay, so and we know, let me just see here. Okay, so the y squared, that's going to be met. In order for this gradient of the potential function equal the vector field, we have to set the first component y squared equal to the partial derivative of f with respect to x. So that gets us the first equation here. Okay, and then we have to take the second component of the vector field and set that equal to the partial derivative of f with respect to y. That gets us this second equation here. And then finally, we take the third component of the vector field and set it equal to the partial derivative of f with respect to z. Okay, that'll give us this third equation. Because again, all three equations, 1, 2, and 3, have to be true so that the gradient of our potential function is equal to our vector field. And we want to find f. We want to find this potential function. And we know it exists because we're told it exists. Please let me know if you have any questions. Hold on. I don't know. I might have been off a little bit here. So again, what we're trying to do, I'm not sure. Let me just repeat what I had said here. So, okay, we're using the first equation. Okay, we're using the first equation. The partial derivative of f with respect to x equals y squared. Okay, that's what we're doing. And when we integrate the partial derivative of f with respect to x, when we integrate that partial derivative with respect to x, well, the integral of a derivative is just going to give us the function back. So that's why we have this function here. But you have to integrate then the y squared with respect to x. You have to integrate the right-hand side with respect to x. So that gets you y squared x plus g of y of z. This is the most general antiderivative, the most general. Okay, you want the most general antiderivative. If you differentiate y squared x plus g of yz, if you differentiate this right-hand side, you're going to get y squared. So it's all correct. Alexander, do you have any questions on that? I'll just query a few students here. How are we doing with that, Alexander? Are you good so far? All right. Lexi, how about you? Are you good with that? Okay, you're fine. All right. Matthew, how about you? Wonderful, wonderful. Okay. Are there any questions before I go on here? Who's feeling good so far? Give me a thumbs up if you're feeling good. If you're feeling good so far. Okay, Shvia's good, Yeva's good, Norina's good. Wonderful, wonderful. Okay. Well, now notice we have three equations here. One, excellent, Simon. Simon's good too. We've used the first equation. And right now, what we have, right, is we have a function, we have our potential function, but we can't use it yet because we do not know what this, this g of yz function is. We have to figure out what that is, right? Well, we utilized already the first equation, but we still have two more equations here that we want to make use of. So what if we were to what if we made use of the second equation? The second equation is a partial derivative of f with respect to y, and it equals 2xy plus e to the 3z. What we can do is we can take our potential function f and differentiate it with respect to y, and then compare that to the second equation here. So when we do that, okay, when we differentiate this equation with respect to y, we're going to get that the partial derivative of f with respect to y equals 2 times y times z plus the partial derivative of g with respect to y. Okay. Notice I don't write this here. This is not g prime of y. Okay, not g prime of y, because g is a function of y and z. So when you differentiate it with respect to y, it's a partial derivative, and I'm using that notation appropriately. I believe, Alexander, you might have had a question on that at office hours. If I'm not, or so far, are you comfortable, Alexander? Okay. Well, at any rate, here's where we're at. Here's where we're at. What I'm going to do now is I'm going to compare the second equation. So what was the equation 2? Equation 2 was this one. The partial derivative of f with respect to y was equal to 2xy plus e to the 3z power, right? That was equation 2 from the previous page. So we're going to compare that equation to equation 5. And it means then that the partial derivative of g with respect to y would have to equal e to the 3z power. And you notice I'll number that equation 6. It helps a lot when you number the equations. And you can be sure I'm going to be looking for this kind of work and numbering on the final exam. You're not going to just get the potential function in 2 steps. No way. Right? You're going to have to show this work. Okay, so okay, so now this is fine. Now I have my equation 6, but I want to know about g of y is z. So I can take equation 6 and I can integrate. I can integrate equation 6 with respect to y. So the integral of the partial derivative with respect to y dy is equal to g of y. G of y z, it equals the function. Okay, well, I have to integrate the right-hand side too of equation 6. The antiderivative of e to the 3z is e to the 3zy plus h of z. It's the most general antiderivative. Okay, and if you differentiate g with respect to y, you're going to get e to the 3z. Okay, so we're good. So far, we're good. Now, the potential function, you have more information about it. The function f, the potential function, would equal y squared x plus e to the 3zy plus h of z. So all that's left now is to determine about that h of z function. So what equation are we going to have to use? What are we going to have to do to this potential function? Which of the 3 equations, for original equations 1, 2, and 3, which of the equations have we not used yet? Have we not utilized yet? That's right, Norina, the third equation. And the third equation, equation 3, here, maybe I'll put that, just kind of set that. So equation 3, I'm just moving that out. Equation 3 was that the partial derivative of f with respect to z was equal to 3 times y times e to the 3z power. Okay, so I'm going to take the potential function and differentiate it with respect to z. It's similar in a way to, remember the method of Lagrange multipliers. You have to utilize all the equations in Lagrange multipliers. So, yeah. Okay, so if we do that, well, is everybody good so far? Are there any, who's feeling good so far up to now? Okay, Yeva's good. Matthew's good. Wonderful. Norina's good. All right. Logan's good. Wonderful. Okay. All right. So, well, all right. So we take that potential function f and we differentiate it with respect to z, and that's going to give us then equation 9. Now when we differentiate the function h of z with respect to z, that's just a regular derivative. It's not a partial derivative. So now, again, we have our partial derivative of f with respect to z, and we're going to compare that with equation 3. Remember, equation 3, I'll rewrite it here. Okay, equation 3, set that off. That was partial derivative of f with respect to z equals 3y times z to the 3z power. So we compare equation 3 with what's above here. So we can learn about, well, h prime of z would have to equal 0, and therefore h of z equals k. And now you've done the most you can do. Now you've determined your potential function. Well, of course, what's k equal to? It turns out that k is not going to matter. K could be any constant. Without loss of generality, you can just have it equal to k. Absolutely fascinating, really. Absolutely fascinating. Please let me know if you have any questions. We're not done yet. We have to now find the line integral, the value of the line integral, using the fundamental theorem of line integrals. But of course, before doing that, we had to identify the potential function. Now we know what it is. And this is the kind of work I would want to see on your final exam. Step by step. Okay, so we have the potential function. And we're ready to compute the work. We're finding the work that the vector field, that our vector field F does in moving the particle along that line segment. So, okay, here we go. Now, by the fundamental theorem of line integrals, this is the fundamental theorem of line integrals. The line integral of the vector field given by the gradient of f over a curve C, along a curve C, is computed by evaluating the potential function at the beginning and end points of the curve and taking the difference. We know that our vector field f is equal to the gradient of f for our field because we found a potential function. So by the fundamental theorem of line integrals, FTLI, the work done in moving the particle along that curve given by that line segment from 0 to -1 to 5, -1, 1, okay, is simply found this way. Let me give you a moment to copy. Please let me know if you have any questions. Okay, so I want to say this the right way. So our space curve C is that line segment. And you know that from section 13.2, that for a line segment C, the R of t is equal to 1 minus t times R0, which is the starting point of the line segment, plus t times R sub 1, which is the ending point of the line segment, where t is between 1 and 0. How many recall using that on their exam? That formula for parameterization. Sure, Narina recalls that. And you know, the reason it's a nice formula is because you don't have to worry about what t, what's the starting value of t, what's the ending value of t. For any line segment, if you utilize this formula to parameterize the line segment, to get the parametric equations for the line segment, for that, that space curve, t would be between 0 and 1. So the ending point, R of b, in this case, would be the R of 1. And the beginning point, R of a here, would be R of 0 at time 0, right? But you don't need, because the fundamental theorem of line integrals just depends on finding the potential function and evaluating that potential function at the beginning points and end points. You don't even need to to find the parameterization for the line segment. All you have to do is just evaluate the potential function at the beginning point and the end point. You notice in the work here, I mean, in the work, I ended up getting 5 minus c cubed minus 2 times e to the negative third. We ended up getting that for the work, but I didn't have to utilize finding the parameterization of the line segment. Now, if I were to use the section 13.2 formula, okay, so in section 13.2, you had, the work was the integral from a to b of f of r of t dot with r prime of t dt. That's section 13.2. Let me make sure I have that right. Hold on. Right. If you did it using this formula here, you could find the work that way, but it might be difficult. It might be difficult to compute the integral, and you'd have to come up with the parameterization. So for that line segment, because you need to know what r of t is in order to do r prime of t. So in this case, it's much easier to use the fundamental theorem of line integrals. Based on this answer, by the way, based on this answer for the work, 5 minus e to the third minus 2 times e to the negative third power, does the force field help or hinder the particle in moving along its path, along that line segment, based on the work? What would you say? Does the force field, does the net contribution of the force field, is it positive or negative in helping the particle move along that path? That's right, Norina, it's negative. That's a negative value for work there. So if we were to plot this three-dimensional, if we were to draw a picture of the force field, and then that line segment, and the particle moves from 0 to -1 to 5, -1, 1, beginning and end points on that line segment, you would find that overall the field is acting against that movement. So now I'll mention something else while I'm at it here. Are there any questions on the computation here, or what you're seeing here? This part here, is f of 5, -1, 1, right? And then you are subtracting this quantity here. That's just f of 0 to -1. Okay, that's what you're doing. So you plug in the x, y, and z where they go in the potential function and evaluate. In the case, you notice cancel out because you are subtracting the values. Now let me ask you this. We go to the whiteboard. I want to show you something here. Okay, so for this example, and it corresponds with example 5 in your section 13.3, but for this example, okay, here was the starting point, 0, 2, 0 to -1. And here's the ending point of 5, -1, 1 for this curve C. And we computed the work. Let's say you took a different path. Let's say this was your path. We'll call it curve C2. So maybe I'll call this C1, okay? And I'll put this on the side. Here's my question. Does this line integral equal this line integral? Okay, you know, there's a vector field F acting here. So in other words, does the work that the force field does in moving the particle along that C1 path equal the work that the vector field does in moving the particle along that other path C2? That's right, Lexi. The work is the same. Very good. And that's because we have a conservative vector field. The vector field F is a conservative, don't want things to be too cluttered here, conservative vector field. So all that matters in computing the work is the starting point and the ending point of the path. So we have independence of path. It doesn't matter how you get from that point 0 to -1 to the point 5, -1, 1. It does not matter. And in fact, we wouldn't even have to say that we have a line segment going from 0 to -1 to 5, -1, 1. If we just said that find the work that the force field does in moving the particle from 0 to -1 to 5, -1, 1, and they didn't specify the path, it would be okay. All right, that's a very, very important concept, a very important concept that you should get out of section 13.3. Okay, are there any questions? I'll mention, by the way, if the vector field F were not a conservative vector field, then the path would matter. And in that case, you know, I'll mention this. Then you would have to compute the work using the definition you learned in section 13.2. And that definition involves the path. That definition, what I'm trying to say is this definition of work from section 13.2 hold on. Let me write it a little more clear here. Dot product there. Okay, this definition of work from section 13.2 is a general, it can be used all the time. But again, when you have a conservative vector field, you can use the fundamental theorem of line integrals. But when you don't have a conservative vector field, you have to use this formula. And you notice in the formula, what do you have in there? You have the path R of t. And R prime of t is dependent on R of t, the path. So there, that definition of work, that depends on the path, you see. So again, if you have a conservative vector field, the work along any path would be the same. But if the vector field F is not a conservative vector field, then the work along one path would be or could be different than a work along another path. And well, yes. Okay, are there any questions on that? Give me a thumbs up if you're feeling good. I always like to end recording. All right, good, Yeva, good, Matthew. Good, Arian, good, Norina. Hopefully this was a helpful example. Good, Logan, wonderful. All right, good. Oh, wait, we have a few more. I always like to include folks, you know. Good, Grayson, very good. Okay, I'm going to stop the recording.